Welcome to Mastering Solutions. This question isn't especially difficult, but it does require a lot of organization just because there's a ton of plug and chug in this question. And so just be very thorough as we go through this to make sure that we're staying organized so you don't get confused and lost in all the numbers. Let's draw a picture of what's happening first. This is a thin film question, of course. And so we have our air up here because it says a thick layer of oil on a sheet of glass. So the air on the top has an N of 1, of course, and then the oil sitting on top of it, they tell us the N is 1.42. Down here is the glass, and glass has an N of 1.50. Now, as light comes through here, some will be reflected off, but some will be refracted. And we're going from a lower to a higher index of refraction. So there will be a phase shift right here. Now, same thing, some's going to get reflected here. And then that going down, and we're going from lower to higher again. So we have a second phase shift. So for this situation, the phase shifts are 2. And we have to figure out the visible wavelengths that interfere constructively and the visible wavelengths that interfere destructively as well. What equations are we going to use? Let's do this side as constructive, and then over here we have destructive. When you have 2 phase shifts and you want constructive interference, the equation that we'll be using is lambda is equal to 2nt over m. When you have 2 phase shifts and you want destructive interference, what we have is lambda is equal to 2nt over m plus 1/2. Now what I've done is I've rearranged the equation for you already. What it's coming from is 2t is equal to m plus 1/2 times lambda over n. And then, of course, this equation here comes from 2t is equal to m times lambda over n. So don't get confused. I just rearranged it for us. And now one important point to remember for both of these is that for constructive interference, the possible m's are going to be 1, 2, 3, just whole integers up from 1. And destructive interference, the possible m's start from 0. And so we have 0, 1, 2, 3, etc. in whole integers. They tell us in the question as well that the T, or the thickness of the oil film, is equal to 500 nanometers. So 500 times 10 to the negative 9 meters. And now as we look at our equations here, we have everything. We have the N of the thin film. We have the thickness of the thin film. Now, what are we trying to do? We're trying to find the different wavelengths that are in the visible spectrum in the electromagnetic. And so to do that, we just have to start plugging away and start at M1, do M2, M3, and see which ones are in the wavelength and see which ones are in the visible spectrum. And so we have to go until we enter it and leave it. So for constructive, let's start at m equals 1. Let's make a little table. So here is the m and 1. We're going to have theta is equal to 2 times n, which we said is 1.42, times the wavelength, which we said was 500 nanometers. And then all that gets divided by m, which we said is 1. Let's write the equation for destructive interference, and then we'll just use our calculator and just plug them in, changing the m values. So we have 2, lambda is equal to, so we have lambda is equal to 2 times the index of refraction, it's the same, the 1.42. The thickness is still that 500 times 10 to the negative 9 meters. I think I might have said this was lambda. This is just the thickness of the thin film. And then we're dividing that by, in this case, we're not starting at 1. We are starting at 0, m of 0. So in this case, it's m plus 1/2, or just a half for the first one. So when we plug this into our calculator, we have 2 times 1.42 times 500 times 10 to the negative 9 for the thickness of the thin film, divided by 1 in this case. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 1420. So M1 is 1420 nanometers. Visible spectrum is 400 to 700. So this is not visible. Let's keep going down. So when we have our next one, we're going to divide that by 2. So now we have 710. M of 2 is 710 nanometers. Close, but it's not in the visible spectrum yet. For 3, same thing. Now we'll divide that by 3, and we have 473. Great. So now we are in the visible light spectrum, nanometers. So there's that one. So 473 nanometers. And now let's keep going to see if there's any more. Divided by M for 4 and 355. So now we are out of the visible light spectrum. So for constructive interference, we only have one wavelength, 473. Okay, so now we can do the exact same thing for part B and plugging in our values here for destructive interference. So let's start with M equals 0. So we have lambda is equal to 2 times 1.42, the end of the thin film, times 500 times 10 to the negative 9 nanometers for the thickness of the thin film, and we'll divide that by M plus 1/2. So we have 0 plus 0.5. So we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 22,840 nanometers for the M of 0. Obviously, that's not in the visible spectrum. Now let's do M of 1. So M of 1, we're going to change this instead of 1/2. We have 1.5. And so that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 947 nanometers. And that's not in the visible spectrum yet, 400, 700. And let's continue on to M of 2. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So 568 nanometers. That is in the visible spectrum. So we're good there. What about M of 3? So we have 3, that's 406 nanometers. So that is in the visible spectrum. And then let's keep going. 406 is almost out of it, so this last one likely won't be for M4, but let's just check anyways. So we have 4.5, and that is 316 nanometers. So yeah, so now we're out of the visible spectrum again. So for constructive interference, the wavelengths will be 473, and destructive interference we have 2. We have 568 and 406. Now, the last part of the question for part C, they say, what color is the reflected light? Well, the reflected light is going to be the 473. So that's a bluish color. And so that's the reflected light for constructive interference. Then what color is the transmitted light? Well, 406, that's also a blue, that's getting into the ultraviolet. So really, I guess that would be more like a purple. It's almost out of it. And so how much would you see of 406 nanometers? Maybe not a lot. So it's probably mostly going to be the 568. And that is a yellowish green. Yellowish green. And so that's the color of the transmitted light, mostly yellow-green and maybe a little bit of purple for the destructive interference that is the transmitted light.